Okay, hello fellow prisoners, Mr. McNeil's class. This is my first video that I'm doing. I've already screwed it up once, so we're going to try to do this again. We're working on problem number 1. Well, not number 1. We're working on the problem at the bottom of the page of the first thermal property of matter worksheet that we have right here. And the question goes something like this. St. Vrain Power Plant was the first nuclear power plant that was later converted to use carbon-based fuel. Happy us. The main water tank is 100,000 liters. That's that right there. 100,000 liters for the main water tank, which it draws from the Platte River. Nobody really cares about that part, but it's a nice detail anyway. Consider the water to be around room temperature. 293 degrees Kelvin is what people have decided room temperature is. And then use the energy densities to determine the amount of fuel needed to boil off the water. Specifically, we're going to be doing number 4, uranium, because I like working with uranium, as culturally insensitive as it might be, seeing as the Japan issues with their nuclear power plants. Anyway, thoughts and prayers go out to them, totally random rant. But you have to figure out a couple things in order to do this equation point. For those who don't know, boiling point in Kelvin is right here, 373 degrees. That's when water boils in kelvins. And so you have to use this cool little equation, which is Q equals mc times delta T. This is heat. Q equals heat. I'm not going to write that down. But Q equals heat times mass times C. C stands for the specific heat constant. Forgot that last time. Constant. Times the change in temperature. Delta T is change in temperature. So, what we do is our mass is really easy. 1 liter weighs exactly 1 kilogram. The British were very nice when they invented the metric system and gave that to us. So we have 100,000 as our mass. Then the specific heat constant, these are usually things you have to look up on the internet, but I'm a nice guy and I looked them up for you guys, so I'm just going to tell you right now, water's specific heat constant is 4,186. So you have that there, and then you multiply it by the change in temperature. A little SL math will show you 373 minus 293 equals 80. So there's change in temperature, and that's just the equation that we plug in. Now when we plug that into the calculator, nifty little thing, you need one of these in physics, you get a really big number. In fact, the calculator doesn't even bother giving you all of the numbers. It says 3.3488 e to the 10th power. I converted that out into nice long numbers just so you people realize how huge it is, and it's 33,488,000,000 true, I think, newtons required. That's an N for newtons. Required to heat this big old tank of water from 293 to 273. Now the second thing that you have to do, now that you have it at boiling point, good for you, you've reached boiling point, it still needs a little additional energy to convert its matter from its liquid state to its solid state. And for that, we have another equation, also using Q. I'm calling it Q1 to try to keep it simple. Q1, they're all over here. But it's Q equals mL. This does not stand for milliliters, this stands for mass. Just like this, mass, times latent heat. Latent heat is another heat constant that usually you'd have to look up, but once again, I'm nice and I've looked it up for you. And so once 100,000 times the latent heat of water, which for water is 2,257. And you end up with this cool little number, 2.257 to the 8th. Or times 10 to the 8th. I don't know. This is how the calculator does it. I know I should be doing right. I should be doing correct scientific notation, but I'm a little too lazy to do that. Let me show you all of the zeros. It looks like they kind of slid off the page. Hooray! There we go. We're good. And so, from here, you get this nice number, which is 225,700,000. Now you simply add these two together, right down here, using, once again, that really handy SL math, and you end up with 33,713,700,000 newtons required to heat this big old tank of water up to its boiling and boiling over point. Now we've decided that we're going to be using the refined uranium, which, as you can see up here, gives off roughly 3,456,000 megajoules per kilogram. Now, since we want to know what it is in joules, you get to multiply that nifty little number by 1,000. So, yeah, I'm running out of room. We'll just do it down here. Scoot this up. Actually, you know what? We can just move this. It'll work just as well. Wow, I'm changing things. Sorry. Let me arrange that. There you go. Now you can see the awesome bottom of the page. It's not all that great. And so all you want to do is divide this number by that number. Now, as I said, we're going to multiply this by 1,000 to get the normal joules. And then you're going to end up with, let's see, 33 billion. Ooh, billions and billions of stars. Never mind. Carl Sagan reference. 700,000. Crap, that's not supposed to be a slash. Ignore that. That's a comma. Newtons divided by 4, 5, 6. And if you give me a second, I'm actually going to pause this.